We're traveling 1,000 light-years from our planet to an unfamiliar system. Here, there are two bright stars orbiting close to each other. But there is one small but very massive thing here as well – a black hole. These objects are mysterious and dangerous. They're capable of swallowing our entire world in 1 second without even noticing it. Even more, they can tear apart a huge star like our Sun. And it's these giants that usually lie at the centers of galaxies. They're so heavy that their gravity holds countless stars, planets, and stardust around them. They can weigh millions or even billions of times more than the Sun. And now, you're back on the ground, at a rocket launch pad on Earth. All you can think about is holding your breath and jumping into the heart of that black pearl. But you don't have to hold your breath because you'll be in a spacesuit, and the oxygen is included free of charge. Besides, you're not likely to ever make it to the black hole. A trip that far with the technology we have now would take tens of thousands of years. Back to your garage where you stashed your hyper rocket, which will take you to the black hole in seconds. And you're next to two stars in a black hole. First thing you notice is that the black holes aren't black. Its gravitational force pulls in not only objects, but even light itself. This makes the hole invisible. You can only see a bright ring around it. That's called the event horizon. It consists of twisted light, hot dust, plasma, and pieces of asteroids that are also trapped there. So the event horizon is the first obstacle to overcome. Okay, you put on your jetpack, open your rocket's door, and jump towards the black hole. The force of gravity begins to pull you quickly toward it. The spacesuit protects you from the enormous temperatures and levels of radiation on the event horizon. Conventional protective gear would hardly help you, so you thank your dad for stashing this super powerful protective suit in your garage as well. You begin to feel like your body's stretching unpleasantly. The problem is that gravity increases with every inch closer to the center of the black hole, and it's much stronger at your head than at your feet. Your body starts to stretch like spaghetti. That's why it's called spaghettification. No suit can protect you from that, and there isn't a single spaceship that can withstand that kind of strain. Well, this was a short video. Okay, let's rewind to the moment before the jump. You realize that to get to the heart of the black hole and survive, you don't need improved equipment, but another black hole. And it's the size and weight of it that matters here. Theoretically, you can survive falling into a supermassive black hole. It's all about the width of the black hole's event horizon. When a hole is small, about the weight of our Sun, the event horizon is small too. And then its edge is remarkably close to the center of the abnormal gravitational force, which would make you spaghettified quickly and brutally. But if the event horizon is wide, it's farther from the center of the gravitational force. Then the difference of gravity pressing on your head and feet will be non-existent. So if you have enough air in your spacesuit, you can survive such a journey. So you must pick a supermassive black hole. Let's see. One at the center of the Milky Way? No, there's too much hot plasma and debris around it. You need a completely isolated black hole for a jump like this. Somewhere in dark space where it hasn't had time to gather the debris of neighboring worlds around it. You quickly open your space map and find such a black hole. One faster than light trip and you've arrived. There it is! A huge dark nothing. There's only distorted light from distant stars and galaxies on its event horizon. To test your theory, you throw a mannequin into it. It approaches the black hole and then slows to a standstill. But it's just an illusion. The black hole is so heavy it can warp both space and time. So to the observer, the dummy is frozen in the event horizon, but it has long since entered its heart. The dummy didn't get spaghettified like you did when you fell into a small black hole, so now you're confidently jumping after it. Remember that even if you feel fine, it's still a one-way trip. Once in the black hole's field of attraction, nothing can escape its embrace, no matter how powerful a rocket you have or how hard you flap your arm. You're now at the edge of the accretion disk. Every second here equals weeks or months on Earth. You're traveling through time. Our home planet may already have flying cars and skyscrapers several miles tall all over the place. But for you, it's only a couple of minutes. Whoa! All the light you see from the stars has turned red. That too is because of gravity. The light we see is waves, but the black hole stretches them out. The short wavelengths of blue become long and red. Great! You've passed the event horizon and are now heading into black nothingness. You look up and see a thin ray of light. The last thing you see, in fact. After that, there's just black void. No one knows what happens next. Some theories say black holes can be portals to another dimension, or to another place in the universe. By jumping into a black hole in our galaxy, you can jump hundreds of thousands of light years away from our home. In that case, you will experience your fall in reverse. First, you see a small but expanding beam of light. Then, red starlight returns to blue. And before you know it, you're back on the event horizon. And soon after, you're free of the black hole's pool. But scientists still can't confirm this theory. Okay, that's too grim. So just this time, we'll bring you back to Earth in the company of your friends. They praise you for your accomplishment of surviving the center of a black hole. Now you're the heart of the company, and no black hole can scare you. But even the biggest black hole in space isn't as scary as you might think. They have a lifespan. That radiation I mentioned takes energy from the black hole. If it doesn't have food around it, the hole starts to deflate like a balloon. And eventually, there's nothing left. Another fear around black holes is that we can create one at home. Indeed, inside the Large Hadron Collider, scientists conduct experiments with small particles colliding at high speed. There are huge bursts of energy, and some scientists believe this energy is enough to create a microscopic black hole. It will begin to absorb its surroundings and grow. First, some small objects in the room where it was created. Then, the entire lab. The hole continues to grow and is already consuming our whole planet. It changes the balance of power in our solar system and absorbs the planets one by one. When those are finished, it's time for dessert, the sun. The light upper layers of plasma are stretched into long spaghetti and pulled toward the black hole. Then, layer by layer, our star collapses into the dark abyss. When the sun is half absorbed, the black hole shoots a beam of energy and light outwards and continues to consume the sun. In mere moments, there's nothing left of our solar system. That's how some people describe the end of the world. But even if we do manage to create a microscopic black hole, we'll be safe. It'll be too small to absorb big objects, and it will only feed on small atomic particles. Black holes emit energy as well as consume it, so our little one won't have time to grow. It'll lose more than it finds in a fraction of a second. So what you'll see is a momentary flash and then nothing. Although creating a stable and controlled black hole may even be useful, they emit enormous amounts of energy that we can use. A black hole the mass of Mount Everest could power all of humanity. Of course, black holes are still dangerous, but we can watch them and study our universe. If we stay far enough away, of course. So, you decide to put a padlock on that garage door. For now.
Here's something cool that scientists have discovered recently. Schrodinger's black holes. Yep, the scariest objects in our universe turned out to be even more terrifying. Now, we know that they can also exist in many states at once. But what does it mean? Let's find out. Black holes are mysterious titans of our universe. Sometimes it feels like the more we learn about them, the less we know. We discovered them quite recently, in the 20th century. And since then, we've been finding various black holes all over the universe. Their sizes range from the size of a small town to horrifyingly unimaginable. But their most important feature is probably their huge mass. And that's where a recent study comes to play. scientists have discovered that black holes have very unusual quantum properties. They found out that each black hole can be both large and small, light and heavy, no longer living and alive. Well, maybe except for the last part. Let's hope that there aren't actually any living black holes. That would be great. But the main point of the discovery is that each black hole can be in all possible states at the same time. It sounds weird, doesn't it? What is it actually supposed to mean? Well, the ability to be everything at the same time isn't a new concept in science. This is what physicists call a superposition, or, to put it simply, a state of uncertainty. Quantum physicists discovered this first in tiny quantum particles. They noticed a very strange thing. As long as we don't observe a particle, it literally exists in all states at the same time. And only when we start interacting with it, for example, looking at it, measuring it, or just doing something, only then does the particle decide what state it should be in. Here's an example of this. Imagine that you have a ball in a box. You don't know what it looks like, and the thing is, as long as it stays in the box, the ball is all colors at the same time. Only when you take it out of the box does it finally choose one color. All this happens instantly, so you don't notice it. For you, the ball has always been blue. Sounds pretty scary, right?
What?
And it raises a lot of questions. For example, how do these particles understand that we're observing them? How do they decide which state to be in? And what does our world really look like if we only see what is shown to us? Of course, this discovery caused a huge stir in the scientific community. No wonder, it does sound a bit unusual. That's what physicist Erwin Schrodinger also thought at the beginning of the 20th century. The ideas of quantum theories seemed delusional to him. That's why he decided to challenge them. He conducted a famous experiment. You've probably heard about it, even if you don't know anything about science at all. Yep, the infamous experiment with Schrodinger's cat. So, what was the point of the experiment? First of all, we have a box and a cat. In the box, there's a container with toxic gas and a special mechanism. Every hour, there's a 50% chance that this mechanism will either open the gas container or not. If it happens, the poisonous gas will be released and the poor cat won't make it. If this doesn't happen, the cat will remain alive and well. Don't worry, this was a purely hypothetical experiment. No cats were harmed in the process. But let's imagine that we did lock a cat in a box and waited for an hour. It's time to check the result. And here's where we get close to the most interesting part. How do you think this situation would end in our regular world? Well, probably within an hour, the container would either open or not, and that would be the moment sealing the cat's fate. After that, we just need to open the lid to find out the answer. But in quantum physics, everything is much stranger. According to it, until we open the box, the cat inside would be both alive and not alive at the same time. In other words, the universe itself doesn't know what to do with this cat. As if the poor animal is on the verge of two worlds inside the box. And when you open the lid, the universe will select a random result of the experiment. So why do we do all this to a poor kitty? Well, initially, Erwin Schrodinger wanted to show how stupid it all sounded, but then he accidentally proved that quantum physicists were right. The situation turned out to be pretty funny. It went like this. Ha ha ha, these quantum physicists have no idea what they're talking about. According to their logic, the cat in my box should be both alive and not alive at the same time. Wait, hold on. Uh-oh, they're right. Schrodinger received the Nobel Prize in 1933, even though it wasn't for this discovery. And in 2022, 3 more scientists received the Nobel Prize for another discovery in this field.
Thank you.
These scientists were Alan Aspect, John F. Clauser, and Anton Zeilinger. They got it for their experiments that involved entangled quantum states. What does all this tell us? Guess now we'll have to look for explanations in some kind of quantum mechanical magic. Unfortunately, humanity isn't developed well enough to test any of these theories. Yet. But we have many cool assumptions. For example, the theory of parallel universes is one of the attempts to explain this phenomenon. Remember that ball in the box? Basically, according to the theory of the multiverse, there's an infinite number of different realities. So if you don't know what the ball looks like, it kind of exists in this interdimensional, uncertain state. But when you open the box and look at the ball, you get transported to a random reality. For example, to the one where it's blue. It sounds pretty incredible, but still exciting. Alright, but why do we need all this info now? Why is it connected to the recent discovery? You see, scientists thought, if teeny tiny particles in our universe behave like this, then what about some giant space objects? And so, they decided to direct their devices not into the microcosm, but into distant space. American and Israeli theoretical physicist Jacob Bekenstein was the first to suggest that black holes may have the same weird properties, but this theory had to be tested. The research itself was aimed at finding a connection between quantum particles and black holes. The researchers created a computer structure in which they placed a simulated quantum particle directly outside a giant simulated black hole. And in the end, this analysis showed that, yep, black holes could also exist in several states at once. For example, they can be incredibly massive and at the same time have no mass at all. And each of these mysterious space gates can have several masses at the same time. The modeling showed that these superimposed masses were, in fact, in certain determined bands or ratios, as predicted by Bekenstein, said the physicist Magdalena Zeik, referring to the study. It's not really clear yet what it all means, and this discovery alone hasn't brought us much closer to understanding how our universe works, or what happens inside black holes. We have realized only one thing. Everything around us is much more complicated and more fantastic than we think. Who knows? Maybe black holes are portals between these parallel universes. At this stage, it's impossible to disprove this. In other words, the universe has once again shown us that it is stranger and more mysterious and fascinating than we could imagine. Let's hope that in the future, we'll be able to understand at least a bit of what's going on in it.
Now, did you know that there's an astronomical object in which space and time actually swap places? How does that work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs? The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you would see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet, the circle of light is growing. It gets bigger and bigger in size until finally it turns into a giant circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we captured the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone, and time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back in time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead, and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Well, take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She can literally influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing, travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends and the slower time goes. What does it mean? Well, for example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity. Right. But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now, imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole. A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend toward the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more, and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it gets so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards. What kind of nonsense is that, you may ask? It'll be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in the spaceship who watches you doing this for some reason. At first, for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything's okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling, all because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place, it's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did. Because in space, you can now only move forward, as if along a straight line. And time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. Why don't you go first? That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side.